So today we're talking about randomized tree metrics. So come on. All right. So what we've been doing. So okay. So starting what last Tuesday we did dimensionality reduction. That was kind of the first thing working with metrics. Okay, and the idea of going down from large dimensions to kind of a nicer, smaller. Their kind of complexity was measured by dimensions, and we're able to get the dimensions low while roughly maintaining the main structure. And then I guess I omitted the LSH slide, but kind of sort of in the same theme, last time we did this L1 metric embedding. So it's a different kind of transforming one metric into another. In this case, uh, we're embedding into L1, which is a sum of line metrics. A line metric is maybe the easiest thing. It's just on a line and some differences. An L1 metric is just a sum of these. And we applied it to sparses cut, uh, because at some level, uh, line metrics are very easy to round for cuts. You can do this sweeping thing, and you actually lose nothing. And what we did was we solved the sparses cut LP, which was a relaxation looking for a metric. Okay, we were looking for like a certain metric as a relaxation of sparses cut, and then we just kind of in a black box fashion converted that into an L1 metric, and we lost the log n factor, right? Because L1 metrics are specific, so you might expect to lose something when you get something back. So you give up this log n factor, but then afterwards you lose nothing. The L1 metric is actually easy to round from a cut point of view, and that was the overall approximation. Okay, so today we'll do something in the same spirit, but a different set of tools. So today we're going to do tree metrics. Okay, so it'll be a different kind of metric, but also with nice properties. So, okay, I think this was already implicit in the last lecture. But a metric has just three kind of basic properties. One, it should be symmetric. Going from A to B should be B to A. Two, it should be positive. Okay, and at least for a strict metric definition, the distances are equal if and only if they're the same point. That's sometimes not the case for us, because vertices might be assigned the same place, and you might want to distinguish the vertices in the original problem, but this is either way not that big a deal. And the last point is the triangle inequality, which you've probably seen before. You want to get from point A to point B. Well, for any intermediate point C, that says, going from A to C as fast as possible and C to B as fast as possible. That gives you one way to go from A to B. Probably, yeah. Okay, UW. I tried to choose the letters that look the same, but you still caught me. Okay. All right. So, okay. Okay, metrics. There's a lot of problems out there that involve metrics explicitly. Sparses cut was sort of implicitly in the relaxation, but explicitly involving metrics. So I have a few examples. So one, okay, let me go through this slowly because there's a lot going on. It's called bias bulk network design, but this was sort of a hot problem in say the 90s when you're building out the internet, right? You're actually laying fiber and you have to choose where to build the fiber and things like this. Okay, so this is how they model it. So you have okay, good. Okay, so you have an undirected graph with some vertices, okay? And every edge has an edge length, L of E, okay? And every edge also has some kind of sub-additive cost function for routing stuff on the edge. Maybe I should go more. So you have edge length, you have demands, point-to-point demands, like, oh, person in California talks to person in New York this much or something. Okay. And so at a high level, you kind of want to buy cable and connect people over the network. Okay. So at some level, you want to choose for every pair S and T a path between S and T in this graph. Okay. But what's your objective? So in this version of the problem, okay, So, uh, depending on how much you use an edge, you have to buy enough capacity for that edge. Okay. So for every edge, let me call U sub E, I'm summing up all the pairs that's using that edge in its chosen path, the capacity, the demand between this pair. Okay. So that gives, by the time you choose a path for every pair and every pair has some kind of demand, that says, oh, that means you have to use that edge this much and that edge this much, that edge this much. Now you put that all together, the total cost will be the length of the edge times some kind of cost per capacity. Okay, some kind of cost per capacity. And so the simplest case is this could just be a fixed amount. So for every mile of this cable that you send some fixed amount of capacity, it costs $10 or something. You double it, it costs $20. So one option is F sub E could be a fixed cost. Okay. The buy at bulk is coming from, well, maybe if you buy a lot of cable, you get a discount for buying more or something like this. So we can make a little bit more general than just like a linear function and allow for a subadditive cost function. So something that's kind of concave and it's kind of sloping. Okay, so it's a little bit more flexible. We're allowing for buy it. Yeah.
So B is like the cost characteristic.
B is how much S and T are talking to each other. So that's like the demand of the network. So ultimately, you can sort of think of it as we choose the paths and then we'll buy the capacity to be able to fit the paths. And then the cost is some kind of discounted thing. Okay? It's some function of the capacity. It'll be monotonically increasing. If you need more capacity along this edge, you have to pay more. But it's possible that the cost goes down a little bit. Okay, it's subadditive. I mean, we want to solve the most general possible problem. Yeah?
So then the cost function, the inequality rule that the effect of y is less than x less than y. Is x and y kind of just like subpats?
These are just quantities. So if x is like 5 and y is 4, the cost of buying capacity 9 is at most the capacity 5 plus cost of capacity 4.
So that UV is the summation instead of like a pat.
Yeah, okay, so the setup is a bit complicated, so I'll go through it again. So basically all you're going to ultimately need to output is for every ST pair, you got to choose one path. You're not allowed to do a flow where you route many paths. Okay, you have to choose one path between every ST pair. And now we got to figure out what's the cost of kind of building a network that supports all these connections. Okay, so fix any edge, which is like an edge you can buy capacity for. And let's look at all the pairs ST where the path you chose for that pair is using that edge, right? So just how much am I using that edge? And what's the total capacity of that edge? Well, it's going to be a sum of demands. So maybe one pair uses 3 units, another pair uses 4 units. So it's going to be a sum. In the simplest case, every pair is using the same like 1 unit of demand, but maybe I'll allow it to be a variable B. Okay. So then I find out a wire I need 10 units of capacity over whatever the length of that edge is. Maybe that wire is 100 miles long or something. And this is FEUE is kind of some amount you're paying per mile. Okay. So you're kind of buying a network and you're doing a network design where you have to route every pair with a single path, and then the total cost has some kind of buy at bulk discount. Okay, or allows for a buy at bulk discount. It could be a linear function. Okay. All right. That's just one possible problem. Okay. Suffice to say, it's also very general, right? The buy at bulk, many things can kind of be put into this decreasing cost function. Okay, so that's one problem. Another problem that maybe you've seen before, the other one might you haven't seen before, is like k-median clustering. Okay, so you have a bunch of points, and so maybe you have a bunch of products in your Amazon catalog, and you just want to group them together or something. Uh, so you try to pick centers, a few centers, so that if you assign every point to their nearest center, like that, right? Something like this. And you're only allowed to open a certain number of centers. Um, you're gonna, for every vertex, you're gonna pay the distance to that nearest neighbor, nearest center. Okay, so the min is over all the centers. So you're just saying get the closest center, pay the cost. Okay, there's another natural problem that's defined over metrics. Okay, you've probably seen this one before. The third example, okay, another complicated one. Metric labeling. So this sometimes comes up in something like uh, computer vision. Okay, so okay, did I do this correctly? Okay, so I think there's a slight typo here. Okay, so at some level in this problem, what you want to do is you want to take some picture before it had the colors and try to kind of divide it up into semantically significant objects. Okay, so how are they trying to model it, at least in this version of the problem, is okay, so okay, so you have all these labels that you can assign, okay? And what are you trying, so you're gonna have to assign for every pixel, which is a vertex in a graph, this could be a graph where you just have adjacent vertices, or you could do bigger neighborhoods or something if you want to do a more complicated model. So okay, so for every pixel, I first have this cost of if I assign this pixel person or something, you pay this much. So this might be some relatively primitive thing just based on the color of the pixel or something, the likelihood of being that label. Okay. The more interesting part is probably coming from here. So for every edge in a graph, which again for a picture might just be neighboring pixels, or it could be neighboring kind of sliding blocks or something. Okay. We can have an edge weight maybe depending on how similar or different the pixels are. Right? The idea being that if two pixels or two spots in a picture are very similar, they're more likely to be the same object. And if they're very different, then maybe they're more likely to be a different object. And so you would adjust the edge weights accordingly. And then we have this metric over. Looks like it should be a metric over labels. Sorry, I think I just wrote all this wrong once. Probably made the same mistake last time. And then a metric over the labels. So what you want to say is something like, okay, if these two pixels are very different, you also have whether or not the labels are very different. Maybe two similar labels are okay to be close, neighboring with a strong edge, something like this. Yeah.
Oh, sorry about the pixels.
Yeah, V will correspond to pixels. In a more general form, you just have a graph with edges, right? Because maybe you want to do like patches of neighborhoods and they're adjacent, and you can generalize this. And then you just have some labels. You're just trying to assign labels. And cost is sort of representing some kind of prior just based on the local information. This is what you get penalized for assigning the label. And then this part is really modeling the adjacent pixels or vertices and some cost. Okay. But this again is a problem about metrics. Okay. Doesn't actually matter too much the details. The only point I want to make is that there's a gazillion approximation problems that are working over metrics and doing some kind of distance stuff. I guess on the list we have other things like group Steiner tree, metrical task systems, vehicle routing. You can imagine a number of routing problems if you're FedEx or something. The K server problem. There's all these kinds of things that where at some level the basic object you're working with is a metric. Okay, so now I want to draw attention to a particular kind of metric. I think last class we sort of discussed shortest path metrics on graphs. This is shortest path metrics on a tree, right? So like what's great about a tree compared to a graph? Yeah, there's no cycles, right? Or like, what makes computing a shortest path non-trivial in a graph? Uh, or yeah. So in a tree, there's only one path between any two vertices, right? In general, any graph problem is interesting insofar as to get from point A to point B, there's so many different decisions you can make. And all these problems are like completely trivial in a tree because there's no choices you can make. Try to find the shortest path to get from A to B. There's only one path to get from A to B. So, for example, if you wanted to get all pairs distances or something, uh, you can do Dijkstra from every vertex or something and run something like mn times. Okay, but like with a tree, depending on your level of comfort with kind of standard data structures, you can build some data structures that let you do things like least common ancestor queries very quickly, right? Like from here to here, what's the least common ancestor? It's this guy. Okay, and you can also combine that with things like uh, what is my distance from here to the root, right? And I can also ask what's my distance from here to the root, and then what's the distance from this least common ancestor to the root, and those three numbers will tell you how to get from leaf to leaf, right? So just with a little pre-processing over the graph, you can answer any pair's distance in like logarithmic time, right? That's just one example of something that becomes very easy in a tree. Okay, good. So all these examples of problems I gave suddenly become very easy or easier on trees. Okay, so if you're trying to do k-meeting on a tree, then you can start thinking about just the edges to remove to separate the clusters and things like this, right? So there's all these strategies you can take on a tree that you wouldn't be able to do in a more general metric. Okay, so trees are nice, and the homework will have some examples of, I think buy a book will be on the homework, and you can figure out how to, buy a book seemed like a very general problem, right? Especially with the discounting cost. Seems impossible, for example, to write an LP for that problem, which is our main technique for doing approximations so far. Yeah, but you can actually do it using tree metrics as you'll explore in a homework problem. Okay, so uh, so what we're going to do in this class is we're going to try to take an undirected graph with some edge weights, right? That could also just be a metric, that's like a complete graph. And we're going to try to compute a tree that maybe contains the vertices of your graph, okay? And we're going to assign some edge weights to that tree. And maybe the cleanest case is, you can try to find a spanning tree even, okay? And you want to try to preserve the distances of every pair of vertices, okay? So in general, all of our metrics, like imagine a spanning tree. If you took a spanning tree of your graph, right? Every pair of edges, their distance only goes up because there's only a subset of edges you can take. So in that sense, our metric will always only expand all the distances and lengths. Okay. So but our question is how much does it expand by? And that's what we want to try to keep down. So for an edge in our original graph, or it could be a pair of vertices in the original graph, we'll define the stretch as the distance in the tree we make divided by its original distance. And our tree distances will always be greater than equal to these, so this will always be greater than equal to 1. Okay? But we want it to be as small as possible. Okay? And let's see if anything is down here. So ideally, maybe we can get something like stretch E for every edge to be, log n, log square, and log cubed n or something like this. And then if you could do that, then we can revisit all these problems from before and hopefully not lose any approximation beyond that because you can do it exactly on the tree. Okay, just like with L1 metrics, we got a nice metric and you can do more. Okay, this is sort of like, well, the easiest kind of graph is a tree. If I can take my graph and approximate it by a tree, And then all these graph problems are easy on trees. But the question is, what do we lose turning it into a tree? Okay, good. So, okay, so who want? Let's say I'm constrained to outputting a spanning tree. Can anyone think of a graph where it would be really hard to come up with a spanning tree that got, small stretch for every edge? So you want to think, okay, well, I'm going to give everyone just a moment to think. So I want to try to come up with a graph, okay? Could be complicated, could be simple, where any spanning tree should have bad stretch for at least one edge. Maybe I'll wait for the second person to come up with an idea. Yeah, okay. Okay, so a cycle, I don't know if that's what you had in mind. Okay, why a cycle?
Because we'll always move one edge, and whatever that edge is moved in the distance, that's going to be like n times larger.
Yeah, so if I remove this edge, then this pair of vertices now has to go n minus 1 around. Right, so every spanning tree will be removing one edge. Okay, but it's always going to be painful. Okay, so good. Um, yeah. So cycle is a bad example. Um, yeah, even if you did an auxiliary tree, things would get kind of difficult. So we will also explore ideas where you're allowed to do something like this. You're allowed to maybe build an auxiliary tree on top with appropriate edge weights. So a natural idea might be like, well, can we do something like building a binary tree along the cycle? Okay, we want to make sure our tree metric is still dominating. So maybe this will have like edge length 1 or something. And then we can kind of keep building a tree like this. Something like this. But I do want to make sure that things are dominating. Yeah, so you have something like, okay. Uh, okay. But even something like this is going to start having something like this is going to still do pretty poorly. Okay. Especially because at some level, at some point, you're going to start needing to make these parent edges bigger weight to make sure it's dominating. Yeah.
Can you explain why graph is bad? There's like in the original graph, the largest distance for the opposite versus the is already like
Yeah, yeah.
almost
So mhm, it's true. So the cycle does have vertices at n over 2. So I'm not necessarily trying to maintain the diameter of the graph. So diameter would be something like, well, can I get a subgraph where the furthest distance between any pair doesn't change too much? Here our goal is to make sure that every pair has roughly the same distance. So many pairs may be happy on the cycle, but that one edge we omit, they used to be next to each other, and then they became n minus 1. So the worst case stretch over all E is still n minus 1. Okay, so good. Now, okay, so at some level, we can't get uniform stretch over all edges. So there's two different kinds of relaxations. Okay, one is to take the average stretch over all the edges. Okay, so try to come up with either an auxiliary tree or a spanning tree. Um, right? And so this is saying, okay, what's the average stretch over all the edges? Yeah.
if you try to do it without a spanning tree, just any tree, they could use that instead.
Uh, yeah, so it's deterministic, you still can't.
Would it still fail on the cycle?
I mean, yeah, the answer is yes. But even in this natural design, if I had more room for more vertices, okay, so as this kind of tree got bigger, you would want to make the edge mates bigger to make sure you still have a dominating metric. Okay. So I don't have a great impossibility proof, but so if you've done a tree like this, the parent edges are going to get bigger and bigger. Okay. But the opposite ends of your tree, because it used to be a cycle, right? So from this extreme end to the other, which is going off the side of the thing, that'll be paying, distance n, where it still used to be distance 1. So at least that design of trying to build just a tree on top and having increasing edge weights won't work. All right, so okay, now so one notion is the average stretch over all the edges. Okay, and if you actually look at our cycle example for this notion of average, we're not doing so bad. Okay, because all of these edges in the graph actually have stretch 1, and only one of these has stretch n minus 1. Okay, so the average stretch here in this notion of the worst stretch is actually a little less than 2. Okay, because that one bad edge gets spread out. Okay, so you can actually find a spanning tree. This is by Alone, Peleg, Karp, and West. Karp, the same Richard Karp from P versus NP. Alone is if you looked at the probabilistic method. And so they have a deterministic algorithm, therefore we won't talk about it in detail, that can get some subpolynomial thing. Okay, it's a region growing algorithm, but okay. Okay, now the other notion we'll look at, so is not a spanning tree. Okay, so we've already introduced this idea, but we're going to try to build an auxiliary tree on top of our graph where the original vertices appear at the leaves. Okay, so blue here is supposed to be the original graph. Red is some kind of auxiliary graph tree built on top. Okay, so if I want to approximate the distance from this vertex or this vertex, I will follow the auxiliary tree. Okay, now we're going to make sure it'll come out naturally in the algorithm that the distances in the tree are always dominating the distances in the graph. Okay, and then we're going to focus on a different notion of average. Okay, so our construction is going to be randomized. And we want to make sure that for every edge, its expected stretch is small. Okay, so any single tree is going to mess up some edges. But every edge on average, if I had run this tree many times, is going to be okay. Yeah. And it works on weighted graphs. It works on actually any metric. So this could just be a generic metric down here, and then, yeah. You can think of a metric also as just a complete graph with the edge length equal to that distance. Okay, good. And I don't think you can do better if it's unweighted either. Yeah. Okay, good. So, all right. And the particular kind of metric we're gonna make, this is sort of a detailed point, low level point, is going to be kind of very structured, where every parent edge will go up by a fixed power. Okay, so maybe the first level edge will be like 1, the next will be 4, next will be 16. I think actually in the original paper they did 1, then 2, then 4, then 8, but having 4 makes the proof a little easier. Factors of 4. Okay. But the one thing that's very nice about something like this is that if I want to know like the distance from here to here, okay, then all I really need to know is the parent, the least common ancestor, because the biggest edge is going to basically give you like a factor 2 or something of the total length, right? Because it's a decreasing geometric series on the way down. So all you really need to know is the biggest edge in between 2, and so it's even simpler. Yeah.
Meaning like we can only have like an alpha area tree.
No, so here alpha is meant to be this factor of 4. There's some factor alpha where every edge is a power of alpha. Not necessarily. No, yeah, to keep it dominating. Well, so it doesn't have to start at 1. It could be any other power of alpha. Um, so I think the dominating part is going to just come naturally from the algorithm. It's not necessarily particular to this. That's sort of orthogonal to this point. It's just going to have this nice property, which it's not going to be too relevant to our lecture. It'll be natural to our algorithm. But there are some of those problems on that list of approximations takes advantage of this particularly nice structure. Okay, good. So, okay, so we're going to basically discuss 2 papers. The main paper that introduced kind of the main idea by Bartal, this is the second of kind of 2 papers, was able to get expected stretch of log n log log n. Okay. And actually, part of his motivation was certain online. Maybe this is worth mentioning. Um, Certain online problems, right? Okay, so here's maybe a cute application. You can have online problems like, I don't know, you want to keep finding different distances or something. Do I have enough context to explain this? Okay, so Bartal was partly motivated by online problems, say in graphs or in metrics or something, where you have to make some choices. You have to choose paths and short paths or something through a graph or something, right? Uh, and his idea was to try to approximate graphs by trees, because once you're in a tree, you have no possible unique choice. I mean, that all the choices are unique. So from competitive standpoint, you get a competitive ratio of just 1 on any tree, and then you just lose something from converting to a tree. Okay, and I'm obviously not explaining the details of the exact problems he had in mind, but it's kind of good to know that some of the motivation for these tree metrics wasn't just approximation algorithms, but also online problems, where again, trees have this nice property where, well, all the decisions are unique, so you get a competitive ratio of 1 automatically for whatever particular problem that was at play. In any case, he got this log n log log n approximation ratio, and people even in approximations also immediately recognize the consequences, because suddenly they realize you can use this tree to start solving all sorts of problems. So then there's a huge number of problems where the best approximation ratio is log n log log n. Everyone's like, oh, what the hell is this log log n? Okay, and so then a follow-up paper a few years later, very much building on the same ideas, was able to remove the log n and get it down to log n, and it became a world record holder for like a gazillion problems simultaneously, best possible bound. Okay, and many of those bounds are in fact tight. Okay, so this is some technique that sort of dramatically solved a lot of problems at once because of this hanging log n factor. Um, it's often still called Bartal trees because that was sort of the starting idea. I'll explain the slight twist that removed the log n. Okay, good. So the theorem we're going to show is that you can get log n. Okay? So we're going to try to get some randomized construction that produces some tree metric, a randomized tree metric, where every edge has an expected stretch log n. So I feel like we've mostly been doing jargon and vocab up to this point. It's going to get more colorful now. Okay. Uh, okay. So here's the idea behind the algorithm. Okay, you have a bunch of points, but let's just imagine you're in like the plane, and that's the metric. Okay. And let's say that this whole space has some diameter delta. Okay, so I know the maximum distance between any pair is at most delta. So what we're going to do is I'm going to pick a random center. Okay, and I'm going to draw a ball of maybe radius delta over 4, so diameter delta over 2. Okay. So I'm not sure if that's a perfect one. So radius delta over 4. Okay. And at some level, I'm going to kind of scoop out all these vertices. And then I'm going to pick another center randomly. And I'm going to scoop out everything else. Now, some of these points have already been scooped. So the part you're taking out looks more like that. Okay. And then you'll pick a random point. Actually, the point can actually be already scooped, but you pick another random center, just the way this algorithm works. Okay. No, I don't want to duplicate that one. Again, it'll be something where a diameter goes down by a factor of 2. Okay, so that's sort of centered there. And you're just going to scoop out everything that's sort of in this ball. Oops. That hasn't been scooped out already. Okay, something like this. And you're going to repeat. Okay, and you keep going, and you're going to end up scooping out everything, and you keep going until there's nothing left. Okay, and then you're going to go down. Now, at some level, you sort of clustered everything into these things of diameter delta over 2. So you can imagine trying to basically recurse and start scooping things out of radius delta over 8 and diameter delta over 4. So you have two different choices here. You can do them in random order. You can do the same random order. I guess I'll draw it in the same random order. So this would be something like radius delta over 2 or delta over 8, just like making up numbers, something like this. Okay. And then scoop out another one. Scoop out another one. This is kind of overlapping. Actually, you probably want to go something more this, something like this, and you keep going. Okay, and then you get smaller diameter, and gradually kind of do some kind of hierarchical decomposition where these clusters get smaller. Okay. Actually, it's a little bit misleading. I think what actually happens for this one is actually you end up having two clusters generated by this one. This one will be kind of a child of this center of that parent, and this one will become a child of this parent. Okay. So I don't know. I drew this picture ahead of time. Okay. And now what are you going to do with this? Well, you're going to use this to kind of arrange all the points in sort of a hierarchical tree. So something like this. So the root represents all, remember, all the points are going to end up at the leaves. So the root is like, that's the whole vertex set, and that graph has diameter delta. And then each of the children are representing graphs of diameter delta over 2. Okay. And then that gets broken further into graphs of diameter delta over 4, I guess, delta over 8, and so forth. Okay. And at some level, yeah, I wrote, it doesn't exactly matter, but when I look finally at two vertices, where they are, at some level, we're going to go up and figure out where they were divided and put into two different scoops when they were separated by a scooping process, and just get the diameter of the last graph when they were together, which, if it goes through root, will be diameter roughly delta or something. I guess I described my algorithm slightly wrong because what we will do is we'll actually be going down in powers of 4. So that would be delta over 16 on the next level instead of delta or something like this. Any constant factor will basically be fine. I only chose 4 to make some analysis easy. Yeah.
You mean by we can find a randomly by
Yeah. Okay, so if you look at, I'll choose 2 different leaves this time, like maybe a leaf a leaf here and a leaf down here or something, right? So as that process is scooping things out, it's keeping a lot of vertices together, but it's also separating some.
So when you draw like a smaller separate, the whites I get scooped up and get separated.
Yes, so you can. We're just kind of gradually breaking up the metric into smaller and smaller pieces. So the least common ancestor of these two leaves will represent sort of the last subgraph or the last submetric where they were still together. And say that metric had at that point the diameter was like delta over 16, so they were distance at most delta over 16, and that's basically what we're going to end up reporting up to constant factors from the smaller edges. So really, the distance between two vertices is kind of determined by when they got split up. Does that make sense? Okay, so that's of course maybe some code, at least iron out some details. Yeah.
Do we recalculate the delta based on the smaller balls, or like? Because I'm imagining like if you have 2 points that are like epsilon close to each other, that's much smaller than delta. You could have to like build like a large.
Yeah. So as a post-processing step, if we always went down by this constant factor of delta, you may, for example, get long paths in your tree because nothing's getting separated. But then afterwards, you can just kind of compress this into a single path, so it's not a big deal. Yeah. And in the algorithm, you can smartly kind of skip stuff. But for the analysis, we'll just assume we do the clumsy thing, and then afterwards you can post-process, or if you want to make things a little more slick, you could do that. Yeah. Okay, good. Okay, so here's more details. In fact, there's one detail I have sort of omitted. Okay, so we're going to order the vertices uniformly at random. So random permutation to start, that's the order in which we scoop. And actually, we're going to also sample this parameter alpha. And what we're going to do is instead of doing exactly this radius, for these, divided by 4, the even things, we'll do that sort of planned radius times alpha. So there'll be a small perturbation, a small random stretch in the radius. Okay, but 2 is not going to change too much. And now for every level from the top to the bottom, okay, so L represents something. I think here we're assuming things are normalized, so the minimum distance is 1. So what is this doing? It's first gathering everything within distance alpha times the radius of this current level. But it's removing any other vertex that's already been scooped out. Okay? So just some awkward math notation for this random scooping process. So I think the two points I want to highlight is that we order the vertices once at the beginning, we keep them the same. And then this wasn't sort of in the demo, it's really a randomly perturbed radius. And then you're going to kind of use the CIJs to kind of partition the VIJs and build this tree. Okay. Yeah.
So B's like scooping.
Yeah. Sorry, this is the ball centered at VI of radius alpha 4 to the I minus 1. So B for ball, and that's just all the points that are in that radius. Yeah.
Basically, this really scripting process, like we would have like all the nodes separated because in a tree we have one vertex down the next one like over this is
So yeah, so down at the bottom, because the minimum distance is 1, and you'll get down to radius 1. So down at the bottom, all the vertices will be centered at separated. But is that answer your question? Yeah, so the vertices will be down at the leaves, and these kind of auxiliary nodes don't really necessarily represent nodes in the original metric. So ultimately, when I want to take 2 points, from my original metric, and I want to estimate the distance using my tree, I go to the leaves and I work up the tree. Yeah, so I sort of yeah.
So there's the number of vertices in the tree is the same as the
Yeah, so I think if you're smart about pruning and stuff, like getting rid of the long path and things like this, you'll ultimately have a leaf of n nodes, and every internal node will have degree at least 2 once you prune the long paths. So you'll have, at most n minus 1 auxiliary nodes, so 2n total nodes. Yeah, just because it's a tree with n leaves. All right, so okay. Okay, so that's the whole kind of crazy algorithm. And I should mention that the only difference, or the primary difference between log n and log n is the very first step. So Bartol would reorder the vertices every time, which is probably more natural. And to remove the log n, you fix the same ordering, which kind of feels unnatural in some ways. Okay, and that removed the log n. Okay. All right, good. All right, so let's try to prove the key thing. Let's fix 2 points, okay, and try to show that in expectation, the distance in this tree, in this kind of hierarchical scooping process, is at most log n times the original distance in expectation. Yeah. Okay. Is there anything here? Guess not. Okay, so okay. So U and V are split at some height. Okay. Again, things are normalized so that like you start at height 0 and you go up to height L or something. So if it's split at height K, then what's the distance roughly that we assign to those vertices? 4 to the K minus 1 or 4 to the K or something. Oh, anyway, there's a tilde there, so they're all fine answers. Okay. Now, when it does get separated, it gets separated by some cluster centered at some vertex, right? Where somehow the vertex was able to scoop one and not the other. So yeah, so when it does get split, so the setup's important just to do carefully because obviously it's kind of a wild and crazy algorithm. It's kind of unbelievable that it works. So U and V are split by a cluster centered at some vertex W for some particular radius. And oops. And in that case, if the radius was, say, 4 to the k minus 1, the diameter was 4 to the k, we'll say that W contributes 4 to the k to the tree distance. Okay, so ultimately, one way to kind of think about the ultimate assigned distance is I can kind of sum up over all the vertices W how much W contributed to the distance. So again, a vertex only contributes to some made up word if it was the center that split them up. And its contribution was sort of whatever that radius or diameter was at that point in time. In that picture, W is contributing 4 to the K or 4 to the K minus 1. Okay. So if we can just analyze for any particular vertex its expected contribution, then maybe it'll sum up to something close to what we're looking for. That's the approach we're going to take. Okay. So, okay. So we're going to let W be the Lth closest vertex to U or V. So what does that mean by closest? So you have U and V, those are kind of like the 0 and the first and second closest. And so by closest, I kind of mean like closest to either U or V. So maybe this is the closest one, and this one is the second closest one, and this one is the third closest one. So this is closest in that it's closer to V than 2 is supposed to be to U. I don't know if it shows very well in the picture. Okay. All right. So the claim is that if W is the 10th closest vertex to U or V, then it will be some constant times the distance divided by 10. If it's the 20th, distance divided by 20. That's the key claim that we'll work on. But if that is the case, then how does that relate to our original goal of log n expected stretch? So suppose this were true, that the 10th furthest vertex or 10th closest vertex, whatever, contributes d over 10. 100th, yeah.
It's equally likely for it to be like LDL closest.
That's actually going in greater detail. What I want to do is I want to zoom out. I want to try to get back to this claim, assuming this, and then we'll go into proving this claim. So I think you're trying to figure out why the L appears. What I'm saying is let's first figure out why this claim helps us. Yeah.
All them give it points. So it would be like over all the lengths.
Yeah, so if you're summing from 1 to n, or maybe you skip the first two, so 3 to n, the contribution from the ith closest vertex, we'll apply linear of expectation, and then you're summing over I duv over I times whatever constant. So you'll get your log n times the distance.
What do we mean by contribution from W?
Yeah. So this is important to establish because we're trying to kind of pull apart a complicated algorithm. So we're looking at u and v, and we're trying to figure out the distance that's assigned to u and v by the tree. And that's really dominated by the point in the tree at which they got separated for the first time. So when they got separated, that means that one of them got scooped out by some ball with some center W and some radius R. Okay. So when W is the center of the cluster that separated them, and if the radius was 4 to the k or something, then I'll say that W contributed 4 to the k to dtuv. Yeah. Contribute just some awkward word I made up. Okay. But the point is that only one of these vertices ultimately kind of determines the distance. Yeah. All right. So, but everything's randomized. That's why we want to do this expected claim. If a vertex is the 10th closest, expected contribution, which means it has to be the one that splits it up, is distance over 10. Yep. All right, good. Good. So let's now try to prove this. And then we'll be done. Okay. So W is the Lth closest for some particular value L. And I'm going to say without loss of generality, let's say it's closer to U than V. Otherwise, I'll switch U and V. Okay, so L is closer to U, and it's kind of the 10th closest overall or something. Okay. All right. So what we're trying to prove is a little bit tricky, but we're going to identify two necessary events that might be easier to analyze. Right? Because I mean, a priori, if you're just trying to figure out the contributes, like, okay, there could be all these other points that are closer, that are further. It's a mess. Okay, but we're going to break it down nicely. And maybe you can guess or try to think of relatively simple necessary events in order for W to be the one that splits U and V. Yeah.
The ones that are closer to,
Okay, so it needs to be Y.
well, if it isn't, then there's going to be another vertex that's splitting U and V.
Yeah, so that's number 2 here. So it needs to be ordered. So there's other vertices that are closer to U or V. And W needs to be randomly ordered first. Otherwise, that closer vertex for every particular radius will try to scoop out U or V first. Okay? Because it's always the same radius. So the closer vertices, if it's ordered first, will either scoop out both U and V before W gets to it, or split U and V before W gets to it. Okay, so that's where the divided by L is ultimately going to come in. What's another thing? Yeah.
It must be like it's the different distance from U to W must be less than, or no, sorry. When it scoops out the thing, it must be closer to W and actually scoop it out without scooping out the well.
Yeah, so this is an observation about the kind of radius of the scoop. The radius needs to be just right so that it goes in between them. So since it's closer to U, the radius needs to be bigger than U and smaller than WV for some K. Okay. Okay, good. All right, so that's two events that you know, at least look more modest than the original full claim. Now, how do E1 and E2 relate to each other? Like if I knew E1 to be true, does that tell me anything about E2? They're independent. E1 and E2 are independent. Well, this is great because if somehow they weren't, then it's going to be a real hard to analyze these. Okay. In fact, we could probably analyze E2 right now. What is the probability of E2? 1 over what? L. Okay. So 1/2 is already done. Okay. So good. All right. So what's left is trying to figure out E1. Okay. And we're going to break it up into two cases. Okay. So in one case, okay, so what does this say? This says that, oops, UV is greater than or equal to 4 times dWu. So this is how I'm saying that U is pretty close to W. I guess here the ball doesn't matter. Uh, but somehow VU is significantly further. Okay, so UV is the distance we're trying to preserve, but somehow W is much closer to U. It could be on the other side like that as well. Yeah.
Should that be 4 to the K? Like in case
No, it's supposed to be 4. And the other extreme case is that somehow DUV is much smaller than DWU, or it's just smaller. Okay, and this is actually almost a bigger liability. So if this is like this is almost easy, but then yeah, okay, but we'll get there. Okay, so this is the second case, something that looks more like this. Okay, so okay, so let's look at this case. This is where you know W is much closer to U than U is to V. Okay, by some constant factor. Okay, what can we do here? This is sort of guessable. Just gotta do some geometry and stuff. Okay, so assume there's some K, where this is kind of good. Okay, so I'll start with like 4 to the K plus 1. I know that this is at most 2 times dWV just because alpha is at most 2. Okay, so dWV is big. And this is 2 times dWu. I'm going to apply the triangle inequality. DUV. And then finally, WU is relatively small. So this is at most, well, I guess if you're being really careful, you can get it down to 5/2 DUV, but really any constant is fine. That's where we're applying this part. Okay. So what's that saying? So, 4 to the K is basically the, if they separated, this would be sort of the radius, right? 4 to the K or 4 to the K plus 1. And this is the value that you would assign. This is the contribution you would make to U and V. Okay. And you're worried about it being way too big compared to D, U, and V. But what you just showed is that if it's separating, the contribution uh, is at most D, U, V. Okay. So good. That makes sense. So what does that mean? So that means that, so okay, so one way to say is that in this case, the expected contribution from W, right? So you have two events. You have event 1, which is the radius works, and event 2 is that the diameter, whatever falls in, right? So this is bounded above by, if the diameter is good, you're paying at most DUV, maybe 5/2 DUV. And meanwhile, event 2 occurs with probability 1 over L. Okay, so in that case, that's how we get this. Okay. Now let's look at case 2, which I think is a little bit more work. Yeah, should there be a factor of 4 in this case? Yeah, what we can do, maybe we can just erase this 4, and then this will just become a bigger constant or something. Okay. Okay. Now, okay, so in the interesting case, this is sort of the riskier case. Okay. Or maybe I actually want a factor of 4 here. We'll see. So the case that in my mind, is a little bit more dangerous is something that looks like this. Okay. So in this case, what you're worried about, right, is this ball, because W is very far away from U or V relative to the distance between U and V. So this picture is somewhat representative. You're worried about this ball, okay, centered at W, cutting them apart. And because W is so far away from both of them, the ball would have to be really big compared to DUV. Okay, so this second case is where we're more afraid of, because this is the one that generates the huge overestimates, or could generate the huge overestimates. Okay, my guess is that it's only going to help us. Okay, whatever. Okay, so that's, maybe let me bring this picture with me. Okay, so good. Yeah.
Simply pick the scale factors.
Yes. Yeah, that's the one piece we haven't used yet, right? Yeah. But let's take it slowly. The first thing is that the choice of K we want to show is unique. Anyone see, like, say, take this exaggerate, why that might be true? So there's many scales at which W can potentially divide U and V, right? Because there's scoops at every scale. But here we're saying is that the choice of scale K is unique. There's only one K we have to worry about, and then that will make the subsequent analysis a little easier. Does that make sense? Does anyone see at least intuitively why? Well, can anyone want to articulate intuitively why?
W is at most like 4 to the K away from U, and then we have like this given that D is at most like 4 K, and then we got the above that's less than 4 K plus 1.
Yeah, something like that. And I think we'll do it slowly, but it should capture the fact that when W is very far away, and let's say there is something that works, and if I shrink this by a factor of 2, because maybe it's 2 times the radius that, so if you shrink this by a factor of 2, you should be nowhere near U and V. And if you double this by a factor of 2, you should be nowhere near U or V. So if there's some alpha that works for some k, shrinking or doubling by a constant factor should be big because that radius is already big compared to distance of UV. Okay, so I think that's what will play out here. So, okay, let me just do it efficiently. So I think this will be exactly what you suggested. If we go one level up, so a slightly bigger radius, then we'll have something like dWV, which is at most dWu plus dUV, which is less than 4K. Okay, so we know that this thing is at most 2 times 4 to the K. I think this is exactly what you said. And we know this thing is at most that thing. So this is at most 4 to the K plus 1. Okay, so that means that if you stretch the radius by, went up to 4 to the K, it'll swallow everything up. Okay, and then on the flip side, you play some similar game. So you know that dWu, the distance to the closer one, is at least the distance to the big one, the further one, minus this. Okay, and this is at least 4 to the K minus 4 to the K over 2. Why did I write 4 to the K minus 2? Oh, sorry. We know that, okay, maybe that slightly. Sorry, I wrote this, but now I'm a little bit confused. Why did I write this again? Anyone
So what he suggested, which is 4 to the K minus 1.
Okay. But why? Okay, so we have dUV is at most I write dWV. Well, it would be nice if I had this factor 2 here or something. In which case you would get 1/2 dWV, something like this. So I might have messed up the original case setup or something. Okay, but it should be. Okay. All right. In the interest of time, let me just assume the choice of k is unique. Okay, I'm off by some constant factor in my notes or in what I wrote down. I just want to make sure we finish on time. Okay. All right. So now you know the choice of k is unique. Okay. So now what we want to do. Okay. So. Okay. All right. Let's now analyze what's the probability of event 1 happening. Right. So at some level. Okay. So you need to be. So there's W intuitively far away. Okay. And, maybe alpha is equal to 1 is somewhere over here. Alpha is equal to 2 somewhere over here, right? You're choosing a random radius in between. Okay. And the distance between here and here. Now this is sort of on the line from W. So it's not exactly lined up, but by a triangle equality, it's always going to be at most DUV, right? I think I got this backwards for us because we have U closer. Okay. So this is really because dVu minus, sorry, dVw minus duw is at most duv. That's like a triangle inequality thing. Okay. So as far as numerator and denominator goes, numerator I have duv. Okay. And I'm choosing, you know, so this is 2 times 4 to the k, and this is 4 to the k, and I'm choosing something randomly in between. Okay. So I'm choosing out of 4 to the k. Okay. So in other words, if you kind of drew it as a line from W, right? This is radius 4 to the K. This is radius 2 times 4 to the K. Sorry? So this is where alpha is coming in, remember? We do alpha times 4 to the K, where alpha is chosen uniformly at random between 0, 1, and 2. Okay. So out of this possible choice of radius, the width of in which you can actually hit and separate UV is going to be at most DUV. Okay. More precisely, it'll be the distance to the further point minus the distance to the closer point, but by triangle inequality that's bounded by DUV. Okay. So suddenly, okay, so you get something like this. Okay, good. So this is very nice, right? Because you're worried about the really, really big radii that's going to really hurt your distance. But because of this alpha factor, you're also kind of offsetting it. Okay, so the really, really large radii actually have smaller probability of hitting it. You get to divide by 4 to the k. Okay, so when we put that together, okay, so the contribution from W, right? First with probability 1 over L, it comes first. Okay, but now first you have the probability of E1, which is the radius comes in. But then for the contribution, then you give a distance 4 to the k. Okay, so the 1 over L is just from the Lth guy coming first. E1 is the radius falling just right. And here we get to offset the 4 to the k's. Okay. This is less than equal. And you finally get the distance divided by L. Okay. So we put all that together, and that's where you get your expected stretch of log n for any particular pair. Yeah, so that sums up everything. There's no time. I would have, for another example is that you can actually use the tree metric to get you a sparsest cut with log and approximation ratio like we did last time. So, but there's a cute answer to this, so maybe that's fun to think about. Okay, so that's how you get log and approximation ratio for a large set of problems. Yeah, questions. So we know that the choice of k is unique for this particular W. Okay, I know there's a little lack of confidence because I might have goofed some constants, but now if W does split U and V, okay, it'll be at the scale where it's assigning radius like 4 to the k or 4k minus 1. So if it splits, E1 is the event, that's sort of capturing if it splits. And in if it splits, it assigns the distance 4 to the k because that's sort of the scale at which you're working at. So here you have probability of E1 is the distance divided by 4 to the k. But then when that happens, you contribute 4 to the k to the distance. So that's where you actually add the distance in and they cancel out. Good. Other questions? Yeah.
What's the point of event?
So event 2 got us this nice 1 over L, where L, if it's, the 10th closest, that's 1 over 10. because at the end of the day, we're worried about all the anyone splitting these guys and contributing some distance, right? But what we can do is say, what about the closest guy? Well, he's going to get distance over 1 because that's L. Distance over 2, distance over 3, distance over 4. So you get this distance times 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. And so then you end up just getting log n times the distance overall. So for the rest of the analysis, we just said, 10th closest, let's just try to get distance over 10. 20th closest, distance over 20. And this is the part that put everything together. Yeah.
Moving the fixed ordering, give you a log n.
Okay. Okay, so the question is, why does the removing the ordering give back a log n? So that framing is a little bit tough. So at some level, if you weren't doing the fixed ordering, then we'd have to work much harder in the analysis, and we'd argue that after a certain number of steps, the number of vertices has gone down by half, and things like this. And somewhere in that more roundabout and complicated analysis, you'd give up this log. You have to fight to get the log n. It wouldn't be easy. It just happens that with the fixed permutation, we're able to do this. It just has to come first, and that works for all the scales, right? Otherwise, different scales, different orderings, then you have to analyze each scale separately, but then you want to group the scales so you get log n instead of paying number of scales, all this kind of stuff. Yeah.
So basically, when we design UMB, that's when we add like edge.
Yeah. So the kind of diameter at that point is ultimately the distance the tree will assign to U and V. We've been done, by the way. So any other questions? Okay, thank you.